What the hell is entropy? Okay, entropy is a measure of the amount of disorder in a system. For example, if I take these 4 board rubbers, okay, when they're stacked like this, they're in a nice ordered state and their entropy is low. But if I drop them on the floor, they're scattered and their entropy is high. Okay, now I realise that this may be a weird concept. You're being introduced to entropy and it's a strange thing. And you may not understand fully what entropy is, but that doesn't matter, okay? You can still get full marks in your exams, you just need to know the equations, okay? You don't really need to understand what entropy really is. Just know the equations and you can get full marks, okay? Just remember that entropy is a measure of disorder. Okay, now, how does entropy help us? Well, you see what I've written here? A reaction is not feasible or spontaneous unless the total entropy change is positive. So, we need to know what feasible and spontaneous means in the context of chemistry, okay? Now, if a reaction is feasible, also known as spontaneous, see, your teacher may use the word feasible and you might read spontaneous in a textbook. They mean the same thing, okay? Or you might see spontaneous in your exam and you might be taught in terms of feasible. In chemistry, they mean the same thing, okay? They also mean spontaneous especially. It doesn't mean spontaneous in the everyday sense, okay? In the chemistry sense, spontaneous means a reaction is spontaneous if it can take place without the input of energy. Okay. So a reaction is feasible or spontaneous if it can happen without any energy being given to it. Right. So this is where the equations come in. Because if you can work out the total entropy change, if it's positive, it tells you that the reaction is spontaneous, okay? So we're going to do an example here. Ammonia and hydrochloric acid reacting to make ammonium chloride. I should also say that spontaneous in the chemistry context, it means it can happen without any energy input, but it doesn't mean that it will happen, okay? It might have the reaction, it might have a very high activation energy, too high for it to take place. So the activation energy may prevent it from happening, okay? If a reaction is feasible or spontaneous, it just means it can happen. Okay. So let's do this example, okay? Ammonia reacting with hydrochloric acid to make ammonium chloride. We've been given a load of data for the reaction. The enthalpy change, the little underground symbol means standard conditions, so atmospheric temperature and pressure, okay? So the enthalpy change is that. We've been given the standard enthalpy for ammonia, standard enthalpy for hydrochloric acid, the reactants, and the standard enthalpy for the product, ammonium chloride. We have to work out the total entropy change, delta S total, and that will tell us if this reaction is feasible or not. Okay, so let's do it. Right, I've got the numbers here, so I've put it in the calculator earlier. So, we need to know to get delta S total, delta S of the surroundings. So let's work that out using this formula, okay? So, delta S of the surroundings is minus delta H over T, which is minus, delta H is minus 315, so it's minus 315 kilojoules, so kilo times 10 to the 3 per mole. Okay, so that's minus delta H. Got to be careful with your minus signs in all this. There are 2 there, so it's going to be positive. Temperature, standard conditions, 298 Kelvin, 25 degrees C. Okay, so minus minus is a plus, and that turns out to be 1057. 1057. Now the units of entropy are joules per Kelvin per mole. Okay? Right, so we've got delta S of the surroundings, that's that bit. To get delta S total, we need delta S of the system. So we're going to use this formula. So delta S of the system is the S of the products. So the products is just ammonium chloride. So that's 94.6. 94.6. Okay. Products, that's that, minus the S of the reactants. And that's these 2. Okay. So that's 192.3, 192.3 plus 186.8. Okay. Stick that in the calculator and you get minus 284.5. Okay, so we've got delta S of the surroundings, delta S of the system, those 2, so now we can get delta S total. Therefore, delta S total is that plus that. So, whoops, delta S of the system is this, minus 284.5, plus delta S of the surroundings, plus delta S of the surroundings, 1057. So that turns out to be plus, that's bigger than that, 772.5 joules per Kelvin per mole. Okay, so we've found that the change in entropy, the total change in entropy, okay, it has to be total entropy change, is positive. And therefore this reaction is feasible. Is feasible. Or is spontaneous. Okay, and that's how we use entropy to work out whether a reaction is spontaneous or not. Okay, next we're going to talk about the Gibbs free energy, and you need to know one more equation. Okay, what we're going to do now is take these 3 equations, do a bit of subbing in, rearrange them, and we're going to get another equation which is going to involve something called the Gibbs free energy. Okay. So, delta S of the surroundings is this. So we're going to sub this into there. Okay? And we get the delta S total is delta S of the system, plus delta S of the surroundings, which is this, minus delta H over T. Okay? We're going to multiply everything by T. So we get T delta S total equals T delta S of the system minus delta H. Okay? Now we're going to multiply everything by minus 1. So therefore, minus T delta S total is equal to delta H minus T delta S of the system. Okay, now this thing here, minus T delta S total, is called a Gibbs free energy, okay, which is represented by the letter G. So therefore, delta G, or rather the change in Gibbs free energy, because there's a delta, okay? Therefore, delta G is equal to this, delta H minus T delta S of the system, okay? And you need to know that equation. So commit that to memory forever, right now. Okay? So, it's the Gibbs free energy. G. Right. Delta G is delta H minus T delta S of the system. It's important to realise that this equation is derived directly from these equations. It's the same thing, basically, okay? And we can use this equation to work out if a reaction is feasible or not in exactly the same way. With this equation, okay, the Gibbs free energy has to be negative in order for a reaction to be feasible, okay? So I'm going to add to this definition. A reaction is not feasible unless the total entropy change is positive or delta G is negative. Okay? They're the same thing. Like I said, these are the same thing, just rearranged. Because look, if delta S total is positive, in other words, if it's feasible, because there's a minus sign there, and temperature is always positive, then the whole thing, delta G, would be negative. So saying that delta S total is positive and delta G is negative, it's the same thing. So let's prove it. Let's put in the numbers and delta G will turn out to be negative. Okay? So, for this example reaction, ammonia and hydrochloric acid making ammonium chloride, delta G is delta H, which is minus 315 kilo times 10 to the 3 joules per mole, minus T, 298, standard conditions, times delta S of the system. And we worked that out in the first half of the video, and delta S of the system was minus 284.5. Minus 284.5. Okay? So, therefore, delta G equals, so that's minus, I'll just go straight to the answer, because I don't know what I calculated previously. This has a greater magnitude than that times that. It's a minus, and this bit's more negative than this is positive. This whole thing, minus times a minus, is a plus, but it's not as positive as this is negative. So the overall answer is minus 230 kilojoules per mole. Okay? So it tallies up. Delta G is negative. Okay? Which again is another way of proving that this reaction is spontaneous. So you can show a reaction is feasible or spontaneous if the total entropy change is positive. Okay, so you might have to use these equations in your exam, or you might have to use this equation and show that the Gibbs free energy is negative. Both achieve the same thing. They both show that the reaction is feasible or spontaneous. Okay, I want to finish off today by talking about a real world example of entropy in action. Okay, now I realise that entropy is a strange thing, the idea of the amount of disorder in a system, but it has real world consequences, okay? The example I want to talk about is dissolving salt in water, okay? As you know, salt dissolves very well in water. Pour it in, give it a stir, and that salt is dissolving very nicely, okay? Now, this reaction is actually an endothermic reaction. As the salt dissolves in the water's getting cooler slightly. It's a bit hard to tell because the temperature change is quite small, but it is real. When you dissolve salt in water, the solution gets cooler, okay? Now, that means it's an endothermic reaction. And when a reaction is endothermic, delta H is positive, right? So, remember from the first part of the video, for a reaction to be feasible or spontaneous, delta G, the Gibbs free energy, has to be negative. And this is a spontaneous reaction, okay? Dissolving salt in water is spontaneous or feasible because it is dissolving, it's happening, but we haven't added any energy, okay? We haven't given it any heat energy. We've just added the salt to the water and let it go. And the reaction, the dissolving, has taken place. So it is a spontaneous reaction. It's an endothermic spontaneous reaction. Now, I realise this is not an isolated system, okay? The glass is in thermal contact with the air surrounding it, but if we were in a vacuum right now, it would still dissolve, okay? Anyway, so delta G for the reaction is negative, but delta H is positive. So let's ignore this term for the moment. If we look at just delta H, okay, in other words, if you only consider the enthalpy, because that's positive, if we only thought about enthalpy, delta G, if it weren't for this term, delta G would be positive, okay? It wouldn't be spontaneous and it would not dissolve. But it's thanks to entropy that it does dissolve. The delta S of the system is positive. The entropy change of the system is positive. So because T is always positive and there's a minus sign there, this whole thing is negative, and it's more negative than delta H is positive. So the entropy drags this down from being positive to overall to negative. So delta G is negative. So it's thanks to the entropy that delta G is negative and the salt can dissolve. So why is the delta S for the system, why is that positive? Well, remember, entropy is a measure of the degree of disorder in a system, okay? Now, the salt, the solid dry salt, is in crystals, and the sodium chloride ions that make up the salt, they're all arranged in nice neat rows in the salt crystal. That's an ordered system, which means the entropy is low. But as soon as that salt is added to the water, it's no longer in a crystal structure. The sodium chloride ions break apart and are free to move around inside the water, inside what's now a sodium chloride solution, aqueous solution, okay? And that's disorder. The sodium chloride ions can go wherever they want, they can move around freely. And so that's a disordered system. The entropy is high, okay? So that's why the delta S for the system is positive. And that ultimately is what allows the salt to dissolve. It's like kind of counterintuitive for an endothermic reaction to be spontaneous, to have a negative delta G. This is an example of that. It's thanks to the entropy that the delta G is negative and the salt can dissolve in the water. So there you go, entropy in action.